Today, we're going to take a look inside the modern motor car because the Champion Spark Plug Company would like to present a spark in time on the firing line. First, if we can get the car engine out where we can all see it. I mean see inside the engine. A cutaway. Thank you. We can now see a basic purpose of the ignition system, that of producing the spark. Spark, please. That ignites the fuel charge in the combustion chamber. Once more, please. The ignition system must also time this spark accurately, making sure that each piston is pushed down at just the right moment to get maximum power and efficiency. Now, this appears to be a pretty simple assignment. But the job keeps getting tougher as demands increase for engines with more and more power. Faster, able to handle long stretches of turnpike driving at high speeds, pulling heavier and heavier loads. Yet operating economically and reliably. All this means that with higher engine compression ratios, it requires higher voltages to push a spark through greater extremes of pressure. And today's high compression engines must operate through a tremendous range of temperatures, from the melting heat of a long mountain pull to sub-zero winter starting. 12,000 sparks must be triggered for each mile an 8-cylinder car travels. This means that at high speeds, each spark plug must work perfectly, up to 40 times each second. Too fast to see in its machine gun rapidity. And each one of these sparks must be precision timed to an unvarying tolerance of 1/10,000th of a second. No wonder that to get the full efficiency designed into our modern engines, ignition systems must be maintained and serviced properly with good modern equipment backed up by adequate knowledge. What's more, all components of the ignition system must be of top quality. Not only the spark plugs, which operate under great extremes of voltage, temperature, and pressure in a current, but all the parts which work to supply the plugs with their sparking voltage. For the spark plug doesn't make the electricity. That's the job of the rest of the ignition system. Hey, what are you... Oh, you're getting the ignition parts out so you can arrange them in a simple diagram. The battery is the source of electricity in practically all automotive ignition systems. To make a circuit, we need electricity to its destination and a return path to complete the circuit. To simplify wiring, connections are grounded to the engine or frame, and this can always be assumed even though it isn't shown. Of course, this circuit will not work, since car batteries have 6 or 12 volts available, while a minimum pressure of about 5,000 volts is required to push a spark across the spark plug gap. That is why the ignition coil is so important. It has the job of taking the low battery voltage and transforming it into high voltage, high enough to spark across the gap. To make it work, a switching device is needed in the low voltage or primary circuit. When it is on, the low voltage flows through the primary windings in the coil, building up a magnetic field. When the current is switched off, this magnetic field collapses, cutting across the secondary coil windings. This action builds a high voltage in the secondary, whatever is needed, up to 30,000 volts to jump the spark gap. Of course, this all happens extremely fast, and many times each second. Switching the low voltage circuit on and off is part of the job of the distributor, which contains all the mechanically moving parts of the ignition system. Hooked into the low voltage circuit The breaker points make and break the primary current, a timing switch, which is synchronized to the engine's rotation by this revolving cam. To eliminate arcing across the breaker points as they open, a condenser is added, which serves as an electronic spring or shock absorber, soaking up unneeded current. This also helps the magnetic field collapse more rapidly. Here now is a workable ignition system for a one-cylinder engine. But most engines have 4, 6, or 8 cylinders. We'll make it 4 in this case to keep it simple. So we need 4 plugs, each to be fired at a different time in proper sequence. This is the function of the distributor, that of distributing the high voltage from the coil to the right plug at the correct moment. The lead from the coil goes into the center of the cap, connecting to a rotor, which directs the high voltage to each plug in its turn. Since each spark plug fires every other engine revolution in a 4-cycle engine, the rotor and cam turn at 1/2 engine speed. To spread the power impulses evenly, each engine is designed with a definite firing sequence. The rotor fires the plugs in this 1, 3, 4, 2 sequence, for instance, in most 4-cylinder engines. And of course, each plug must reliably get the fire going 7 to 40 times each second, while fighting off punishing pressure blows, searing blasts of heat, corrosive burning gases, and other corrosive deposits which try to short out the high voltage charges and prevent them from jumping the gap. All right, no guillotines. A spark plug leads a tough enough life as it is without overdoing it. And it's certainly no wonder, with all of the extreme conditions under which spark plugs must do their job, that spark plug people must spend so much time developing special electrode alloys, which will stand up under electrical erosion, chemical corrosion, and heat attack. Seals which hold permanently and prevent leakage from extreme pressures. Ceramic insulator materials which can withstand heat shock and high voltages while conducting heat away from the firing tips, and all the other features which give modern-day spark plugs their tremendous dependability. And there must be many different kinds of plugs, designed especially for different types of engines, different sizes, different heat ranges, and a variety of special requirements. And those who want the best in quality know when it's time to change their it's time to change the subject. Speaking of timing, the ignition system not only has to get the spark to the right cylinder, but it must get it there precisely at the right instant to complete burning of the fuel charge, just as the piston has passed the top of its stroke and is starting down. This timing will give the maximum power push from the expanding gases. If ignition is timed too soon and the piston is going up when it meets the power push coming down, disagreement over direction results. And if ignition is timed too late, the push power of the expanding gases is wasted. All right, coffee break's over. Let's get back to work. Though the spark must be timed to the precisely right moment, that moment isn't always the same. So we'll make a simple graph to show, when running at low speed, how much time is taken up by the spark, combustion, and the push of expanding gases, all of which take a fixed amount of time to occur. This is slowed down considerably, of course. When correctly timed, sparking comes soon enough so that combustion is completed at or near the top of the piston stroke. Top dead center, it's called. So the maximum power push coincides with the piston's thrust downward. It's the setting of when the points open that controls spark timing, since this opens the primary circuit, so the magnetic field in the coil will collapse and build a sparking voltage in the secondary circuit. Moving the points changes the timing of when they're opened by the cam. Moving them too far against the cam's direction of rotation will make them open sooner, advancing spark timing to where power is lost. Retarding the spark timing too far also wastes power. So correct basic ignition timing at idling speed is set with a timing light to get the maximum power push. But what if we speed up the engine without changing the spark timing? Since it takes just as long for spark, combustion, and power push to take place, the faster the engine rotates, the more the spark should be advanced. Some means must be provided for changing the timing to suit different speeds and conditions, an automatic spark advance. There are several ways of doing this, each based on changing the relationship of the points in the cam by devices sensitive to the engine's performance. The automatic spark advance only works as needed and doesn't affect basic timing, which remains the same once it is set. It's worth noting that breaker point spacing will affect timing. Each manufacturer specifies settings for what is known as cam or dwell angle, the number of degrees of cam rotation during which the points dwell or remain closed. Adjusting the points to a wider gap decreases this dwell angle. This advances the timing since the points open sooner, and there isn't enough time for the primary circuit to build a good magnetic field in the coil. Narrowing the gap between the points increases the dwell angle, and timing is retarded since the points will open later. If the points are too close together, they carry too much current and tend to burn. That's why careful setting of this precise mechanism is so important to good ignition performance. Here now is the working ignition system. Battery to store low voltage electricity, coil to transform low voltage to high voltage, breaker points to time the collapse of the coil's magnetic field, with a condenser to help it collapse faster, advanced mechanisms to adjust spark timing to conditions, rotor to dispatch the high voltage to the correct cylinder, and spark plugs to fire the fuel mixture. And we should add an ignition switch for turning the system on and off, and perhaps some sort of resistor in the primary circuit, such as are used in many 12-volt systems to cut down the voltage after permitting a higher voltage for starting. These should be included if for no other reason than to remind us they too should be checked as possible culprits if the ignition system isn't working properly. Oh, and one more thing. To suppress radio and electronic interference, ignition systems have resistance built into the ignition circuit, in the distributor, in the ignition leads, or inside the spark plugs themselves. As long as they are in good condition and operating correctly, they have no effect on engine performance. Now let's take a look at the ignition system in another way. All elements of the system, except for the spark plugs, are concerned with providing sufficient voltage at the right time, the job of making voltage available. The spark plugs use this voltage, and their condition determines the voltage required. To relate these two basic functions, we need a graph. No, get him out of here. I said graph. This scale represents voltage from 0 to 30,000 volts. A typical 12-volt ignition system that's new or in excellent condition will make up to 30,000 volts available to the spark plugs, while brand new plugs require about 5,000 volts to produce a spark that will jump the gap. The difference between voltages available and required is the reserve strength of the system. You might call it a laziness factor, since like a strong man or a super mouse who can lift his own weight but doesn't use any more strength than he has to, an ignition system does not produce any more voltage than is needed to push the spark across the gap between the plug electrodes. However, sudden acceleration increases voltage requirements sharply. Ignition systems in top condition have plenty of reserve to handle these sudden loads. But as plugs are used, the electrodes wear and the gap opens wider. By the time they've run about 10,000 miles, the electrodes are burned and worn, and voltage requirements have doubled. And if these plugs are not replaced, voltage required keeps going up until sudden acceleration increases requirements above availability, and the engine misfires. Replacement with new plugs will restore the reserve factor, but there are other conditions which can affect voltage requirements. The sparking end of a plug works where it is constantly exposed to oil and the products of combustion. Deposits may form on the insulator, which, if allowed to build up heavily, give the circuit an easier path to take at a much lower voltage. This spark plug fouling causes the engine to misfire because there is no spark to ignite the fuel, a condition where voltage required, being so lazy it only works as hard as it must to complete the circuit, doesn't build up the voltage required for sparking. We might also mention that if the primary leads to the coil get switched, reversing polarity, voltage requirements will be increased about 40%, which on top of any other adverse factors can soon cause trouble unless corrected. Once again, we have first developed a situation as if for a one-cylinder engine. To get the complete picture, voltage requirements for each cylinder would have to be recorded separately, just as is done on modern electronic oscilloscopes, such as the plug scope, which simplify the job of checking ignition systems. With a graph or trace for each plug, any condition which affects voltage requirements will be reflected on the proper bar. For instance, if a plug has too wide a gap, its trace bar will show an increase in voltage requirements, in this case, bringing it above the reference line, a definite indication of unsatisfactory ignition performance. On the other hand, if a plug is fouled, its voltage required would drop, since what we actually see is the voltage required to leak to the ground, lower than what is required to jump the spark gap. On the scope, then, we can compare voltage requirements for all plugs. Voltage available can also be observed and compared by disconnecting any of the plug leads, thus forcing the lazy ignition system to put out as much voltage as it can. Then we have a direct comparison of available and required. If voltage available is lower than it should be, it is apparent that the ignition system should be checked for trouble. It could be that the breaker points are spaced too far apart, making the dwell angle too small. It could be the condenser. If it is not properly matched to the system, it can cut down voltage available and also cause transfer of metal at the points. The induction coil may be partially shorted. Dirty or burned contacts or connections may be cutting down voltage available. So, as time passes and the ignition system is given a harsh and hectic workout, there are many ways in which available voltage can be reduced, while voltage requirements creep up until our once strong system is sick, and the load it must bear is beyond its ability. Of course, major illness often can be prevented by looking for early symptoms before the illness becomes serious, by periodic checkups and tune-ups, something car owners seldom think of themselves unless it is suggested to them.